The topic of this video is long multiplication. I'd like to show you a nice systematic way of doing the calculation. It's nice because it's easy to do. It's nice because it's easy to check, which is important. You should always check the work. In particular, you should design the work from the very beginning to make it easy to check. The method's also nice because it's easy to understand in terms of things you already know. Nice simple things like place value and the distributive law. This is the second of two videos. In a previous video, we discussed the background and the principles involved and did some simple examples. In this video, we're going to talk about the recipe in all generality so that you can multiply anything by anything. Let's multiply a couple of slightly bigger numbers. This will let us see almost all the features of the long multiplication algorithm. As always, we follow the strategy we discussed in the previous video. We pick apart both factors and proceed digit by digit. We start with the low order digit of the bottom factor, which is that guy. So 1 times 7 is 7, which goes there, lined up under the 1. And 1 times 6 is 6, which goes there. 1 times 5 is 5, which goes there. 1 times 4 is 4, which goes there. We now move on to the second digit in the lower factor, which is that guy. And so now 2 times 7 is 14, which we put here. And it has to go there because of place value. It's lined up with the 2, which is the guy we're working on. Next comes 2 times 6, and that's going to be shifted over one place. We'd like to write it here, but we can't do that because there's somebody already there. We can, however, come down a line and write that there. So as long as it's in the right column, it means the right thing. Next is 2 times 5 is 10, and we can put that there. And last but not least, 2 times 4 is 8, and that goes there. And that completes this group here. This group is the by 20 group. And now we start with 3 times 7, which is 21. And that has to be lined up here. So that's going to go there. So before we go any farther, point out the pattern here, that each of these numbers within the by 20 group is shifted over one place relative to the previous thing. Follows a nice pattern there, and that's just because of place value. Each of these guys is inheriting some place value from where he came from in the upper factor. On the other hand, you shouldn't get too enamored of this nice little pattern because it only holds within the by 20 group, and the actual pattern is more complicated. So you absolutely could write it out this way. One slight problem: we're not finished. We sort of ran out of room down here. And that's because the thing isn't as compact as it could be. Let's finish the problem we started on the previous slide and see if we can do it in a more compact form. As always, we proceed digit by digit, starting with this guy here. 1 times 4,567 is 4,560. I've already done that. So let's move on to the next digit, which is this guy. 2 times 7 is 14. And we put that here, just like last time. And that's lined up with the 2, as it should be. 2 times 6 is 12. And we put that here, just like last time. Next comes 2 times 5, which is 10. And we could write that down here like we did last time, but let's not do that, because there's room for it up here. And as long as it's in the right column, it means the same thing. So that's all good. Last but not least, we have 2 times 4 is 8, and there's room for that there. And that completes this group. This is the by 20 group. So we now move on to the next digit in the lower factor, which is a 3. 3 times 7 is 21, and we need to write that so it's lined up with the 3. So let's write that here. Next comes 3 times 6, which is 18, and we can put that here. Next is 3 times 5, and that'll be shifted over one relative to the previous thing, and there's room for that here. Last but not least, 3 times 4 is 12, and there's room for that there. And that's all there is. That's the end of the multiplying. That finishes out this group here, which is the by 300 group. We finished the multiplying, so all we have to do now is the adding. 7 comes down here. That's easy. 6 plus 4 is 10. Carry the 1. 6, 7, 9, 10. Again, carry the 1. 5, 6, 8. 8 more makes 16. Carry the 1. Makes 2, 10, 15, 16. Right down the 6. Carry the 1. It gives us 2, 4, and a 1. And that's our answer. Let's have a couple remarks here. First of all, part of the strategy we're following here says first do all the short multiplying, then do all the adding. So here are all the short multiplication products all laid out nicely, and after we're through with all that, we do the adding. And that turns out to be important. It makes the algorithm more efficient. It also makes it easier to check, as we will discuss in a couple of slides. It also helps to keep things lined up, as we discuss on the next slide. It really pays to think about these things in groups. By that, I mean this is the by ones group, this is the by 20 group, and this is the by 300 group. Each of these is associated with one of the digits in the lower factor. That this digit gives rise to this group, this digit gives rise to this group, and this digit gives rise to this group. Another thing you notice is that the block is lined up with the number that gave rise to it. That's lined up with the 1, that's lined up with 2, that's lined up with the 3, and that makes sense because the group inherits place value from the digit in the lower factor that owns that group. As a separate matter, within each group, notice that successive short multiplication products are shifted over one place. Here's the first product, here's the second product, shifted over one relative to the previous. This short multiplication product is shifted over another one, and this is shifted over another one. So within each group, each product is shifted over one place, and that's because within each group, it inherits place value from the digit in the upper factor that gave rise to it. So as we go here, digit to digit to digit, you get more place value. Here's product to product to product to product with more place value. So each group here is shifted over one place relative to the previous group, but that's not actually the smart way to think about it. The smart way to think about it is that the group is lined up with the digit that gave rise to it. That'll never get you into trouble. Speaking of trouble, people are really good at noticing patterns, including patterns that don't really exist, like constellations in the sky. So if you just look here, you see a pattern where each row is shifted over one place, but that's going to get you into trouble because you get here, it's not shifted over one place. That's because it's a bogus pattern. That's like a constellation. What's really happening here are the blocks are shifted over, and if the blocks are 2 rows, well, you have to wait a row before it gets shifted over. So the real rule here is that each block is lined up with the digit that owns that block, and then and that's because of place value, and within each group, successive short multiplication products are shifted over one relative to the previous, and that's also because of place value, that the blocks inherit place value from the lower factor, and within each block, successive products inherit place value from the upper factor. It's always important to check the work. Let's check the short multiplication here. Part of our strategy is to do all of the short multiplying first and then do all the adding later. This makes things very much easier to check, because all the short multiplication products are just sitting there begging to be checked. Also, the block structure makes it very much easier to check things. But this block here is lined up, is the by 2's block. It's lined up to 2. So if you wanted to check this 14 here, that's the first product within this block, so it has to come from this 2 and this 7, so that checks. That has the nice property that it allows you to check some subset of the work without having to check every bit of it. That makes the checking more efficient. Also, it allows you to check things in reverse. If you got curious about this 10, wonder where that came from, well, it's part of this second block, so it has to involve this, and it's the third product within the block, so it has to involve this, so that checks. Once again, this allows you to check more efficiently because you can check a subset of the work without having to check everything, and most importantly, you can check stuff without introducing new errors. There are other methods that involve doing the adding as you go along, writing down the carries, crossing out the carries, blah, 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 and that muddies the water, that the short multiplication products aren't sitting there in any natural way. It's very much hard to check them without redoing all of the work, and there's also a chance that you'll introduce new errors. That's a big mess. Last but not least, point out that you can check these things even if you don't have colored ink, using a pretty similar technique. You just underline stuff. For instance, this 6 starts out here, he shows up here, and he contributes here, and he contributes here again. So that's almost as good as colored ink. You just underline him. If you wanted to keep track of this 5, use a double underline. He starts out there, he shows up here, he contributes to this thing, and he contributes to this thing. So once again, that allows us to check things, find out where things came from, where things went to, without introducing new errors. It makes the thing very much more reliable, very much more efficient. It's also important to check the addition. One trick that you can use is to check the addition bottom up. The first time we did it top down. Let's do it bottom up this time. 7 still makes 7. Bottom up, 4 plus 6 is 10. Carry the 1. Plus 1 makes 2, 4, 5, 10. Write down the 0, carry the 1, 9, 11, 12, 16. Working up from the bottom, write down the 6, carry the 1, 2, 7, 15, 16. Write down the 6, carry the 1, 3, 4, and we're done. So the reason for doing it up from the bottom the second time is that the running sums will be different. So if you're a little shaky on your short addition facts, you're likely to make different mistakes each time, and it makes a more reliable check. Also, note that we are using the carries as fast as we generate them, so we don't even need to write them down. We don't ever need to cross out the carries. You just generate them and use them immediately. That makes this algorithm, once again, much more efficient and much more reliable. Let's do one more example here. Illustrates an idea that didn't show up in the previous examples, something you need to do sometimes to keep yourself out of trouble. Same method, we'll pick this apart into digits and start multiplying. 3 times 3 is 9, which goes here. However, I'm anticipating trouble, so I'm going to write that as 0, 9. Moving on to the next digit, 3 times 2 is 6, which goes here, but I'm anticipating trouble, so I'm going to write that as a 0, 6. You'll see why in a minute. 3 times 8 is 24, and that goes here, and that's taken up 2 digits, which is the whole idea here. 3 times 1 is 3. I'm going to write that as 2 digits. I'm going to write that as 0, 3, even though we don't exactly have to. Now we move on to the 2's digit here. 2 times 3 is 6. That lines up under the 2. So I'll write that as a 0, 6. 2 times 2 is 4. That's got to be shifted over one more. So let's write this as 0, 4. 2 times 8 is 16. And there's room for that here. And 2 times 1 is 2. So I'm going to write this as a 0, 2. Now, most of these numbers here, I could have written them as one digit, but I wrote each of them as 2 digits, just so we get this nice alternating pattern. 2 digits here, 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 shifted over 1 each time. Just so it falls into a nice pattern, just so it falls into a nice rhythm, keeps you out of trouble. And now all we need to do is the addition problem. So this 9 comes down here. 6 and 6 makes 12. Carry the 1. We get 5, 9. Okay, 5 makes 11. Carry the 1. This gives us a 4. So that's probably the right answer. So the rule here is simple. Use 2 digits for each product unless you're sure you don't need to, just so things fall into a nice systematic pattern. Systematic is good. Let's summarize what we've discussed. Graph paper helps, especially at first. The best thing is a lab book. Such things are cheap and readily available from office supply stores. On the other hand, once you understand the importance of keeping things lined up in columns, you can discipline yourself to keep things lined up, and then you can do fine without graph paper. The most important idea is that long division can be understood in terms of the distributive law and the axioms of the numeral system, really basic stuff that you already know about. There's a smart method for organizing the calculation. Proceed digit by digit. First do all the short multiplying, then do all the adding. Use columns to keep track of the place value. And that's pretty much all there is to it. Using this method, you can multiply anything by anything.